Today we're presenting on how to optimize an under-the-sink water filtration system. This is Team 4, consisting of Hung-Kai Chen, Griffin Coolidge, Aubrey Kleinsorgi, Kana Moriyama, and Joshua Wong. Our system is designed to take in a normal household's tap water and output a chilled, filtered drinking water, with the mechanisms in between lying within our system boundary. Our first subsystem is a reverse osmosis module that looks at combinations of pre-filters, reverse osmosis filters, and pumps. Subsystem 2 is the tank storage unit with inputs of tank geometry and inflowing water temperature. Subsystem 3 is the post-carbon filter with inputs of the length and diameter of the carbon filter and average particle size of the activated charcoal. All three of our subsystems output a material and maintenance cost averaged over the system's life cycle. Our systems are linked by the water flowing between them. Subsystem 2 will receive water at a rate determined by the combination of reverse osmosis filter and pump from subsystem 1. Subsystem 3 will receive water at a cooled temperature and rate determined by subsystem 2. It is necessary to model this at a system level because even though we can find minimum costs for each subsystem, we want to ensure quality drinking water, which is determined by our selection of filters. We also want to ensure an adequate daily water supply for a typical household, which will be determined by a combination of our tank volume, as well as the water flow from our reverse osmosis module. A high reverse osmosis flow rate allows us to select a smaller storage tank, while a larger storage tank allows us to select a lower flow reverse osmosis module.
Our first subsystem is the RO membrane filter. It consists of three components, which are the pre-RO filter, the RO filter, and the optional pump. Water is driven through the pre-RO filter and the RO filter by the external water pressure. The materials chosen for those two components decides the flow rate of water exiting to the next subsystem. This flow rate can be increased by adding a pump or choosing more efficient filters, but these options will increase cost. The objective is to select these components to minimize total annual cost, including capital spend and operational cost. The subsystem variables that can be chosen are the material ID for each component. These components are all organized into tables with the associated prices, lifespans, and flow rates. For the pre-RO filters shown in the top table, the annual cost is just the price divided by the lifespan. For the pumps on the bottom table, the contribution of electricity cost is added. And finally, for the RO filters, in addition to storing annual costs in the same manner, the exit flow rate in gallons per day was fit to a linear function of the incoming water pressure for each choice of RO filter, with the slope and intercept of that equation stored in the table. The relevant parameters for the subsystem are the minimum outgoing water flow rate and the incoming water pressure. Our optimization was modeled as a knapsack problem where we select from a set number of choices for each component, and ID is the variable. So we have the constraint that all IDs must be between 1 and the total number of choices, and all must be integers. The minimum flow rate is also a constraint, and the objective function that we minimized is the sum of the annual cost of all three components. We used genetic algorithm to minimize the annual cost objective function. For lower flow rates, we found that the optimal solution yielded an annual cost of $68.54 with no active constraints, and for minimum flow rates greater than 82.5 gallons per day, the flow rate constraint was active and annual cost went up as the minimum flow rate increased.
The second subsystem of our model is a refrigeration unit that cools the water before consumption. It consists of a hollow metal vessel where the water is stored, surrounded by insulation on all sides. The cost function takes into account the fixed manufacturing expenses and also the cost of refrigeration. It is lost through all of the sides and also from the exchange of room temperature water with refrigerated water leaving the vessel. We constrained the metal wall thickness to at least 1 millimeter, with the inner volume of the water being equal to 12 liters exactly. Including the insulation, the outer volume must be less than 25 liters. And our algorithm optimizes to have an efficient, low-cost manufacturing build, but also being effective at preventing heat loss so as to prevent electrical costs over time. The most important intermediate value is the radiative heat transfer coefficient, which is different because it depends on the outer surface temperature of the insulation. This is different for each of our different designs since we've experimented with different thicknesses, so this value is calculated in every single cost function. Once this is established, it's a relatively straightforward thermal circuit, so by summing the electrical cost with the manufacturing, we have our answer. This is done in FMINCON and MATLAB, which is efficient for a nonlinear constrained design problem and was very good for my physics-based equation solving. For the first problem with the fixed volume optimizing for cost, we got down to 87 cents per liter. And to experiment for a variable volume for optimizing for cost per liter instead of cost overall, we got 89 cents, which is not nearly as good. So to experiment some more, I made a weighted cost function that weighs ergonomic proportionality with the cost per liter to try and see if I can add value beyond just cost. So these were the results with a variety of different coefficients shown below. And again, they converge to the 89 cents per liter value, which goes to show the algorithm works a bit better when you don't try to experiment with two main variables and instead constrain the volume and experiment with just the cost.
I'll be presenting the post-carbon filter subsystem, which is the final stage of our water filtration system optimization. There are our parameters and design variables. Next slide shows the constraints and objective function. Our main objective was to minimize costs over a standard lifetime of 1 year. However, we are faced a direct trade-off. Minimizing the cost requires lowering the filter length and diameter, which goes against the performance constraints. To build our analytical model, we utilize the Casino-Kalman equation to simulate the flow dynamics. We set performance constraints to guarantee output taste quality and to strictly maintain the flow's Reynolds number within a nominal flow region. Our model relies on a few key assumptions. The flow is laminar and steady state. The carbon has a consistent porosity, and the filtration follows the first order assumption of decay model.
For the post-carbon filter optimization method, this subsystem was a classic nonlinear programming problem. The MATLAB fmincon solver was used because of its ability to accept inputs of nonlinear inequality constraints, as well as lower and upper bounds of constraints with efficient solving time. fmincon also has a tight tolerance, so results are trustworthy. No additional schemes were used. Moving on to the result of optimization, each trial had 5 different initial conditions with no discrepancy between X star and F star. X star values are shown with the total cost F star of $36.60. The active constraints are the diameter constraint and laminar flow constraint. Since there are no discrepancies, this suggests a robust model and algorithm, and that our result is a global minimum. Looking at our data, we can see that the diameter is the bottleneck, and this constraint stops the optimizer from further increasing it. As I previously stated, the L and DP constraints are not active, but the DP is at an exact value which makes the laminar constraint active. Again, the algorithm is robust and optimizations converge to the same results. The final optimal dimensions and resulting costs for this subsystem are as shown, while also reducing contaminants by 90%. Thank you.